And we're now going to hold the last panel discussion of the day with Professor Richardson, Yagi, Dr. Venter, and Bengt Nordén. The afternoon program highlighted the perils ahead for the planet Earth, ways to take action, and new perspectives and tools that can lead to longer, hopefully healthier lives. Please remember, if you have a question, to state your name and affiliation. So, we have some questions that came in through our live stream.
Can't see anything.
And we can start with Catherine. Some critics say that some of the suggested interventions could open up a Pandora's box of new problems. Scrambling weather patterns and amplifying human suffering through unintended consequences. So I guess that could be for both you and Omar, but do you want to?
Yes, absolutely. I think that's exactly what I'm trying to say, because so many of the interventions that are being planned at the moment aren't actually thought into a system context. And we've seen time and time again that lots of solutions, DDT, for example, or CFCs, for example, or right now we're doing nitrification inhibitors, which is, just another pesticide impacting, trying to change the system. Life has evolved for 3.5 billion years to a very fine-tuned system, and then we go in and say, well, we can fix this. I totally and completely agree, and it's the same with most geoengineering, and I'm sorry to say, I'm a little concerned about, and we can maybe get into a discussion or argument about this, carbon capture and storage. Excuse me, isn't that just use and throw away again?
I'm sorry. She's right.
No, you don't have to be sorry. Well, the way I look at it is that, civilizations advance by creating technology to move things forward. It's going to have good and bad side effects. And if we're smart, we can act quickly to remedy some of these until there is an ideal solution, as you are suggesting, Catherine. And we can't wait for an ideal solution. You can't go back that easily and build the balanced ecosystem that you're advocating. But so what and also, I want everybody to think about the secondary effects of new inventions, okay? I didn't target CO2 capture. I targeted creating materials from natural building blocks that will advance our knowledge of matter on the atomic and molecular level, and it will create technologies even beyond what we can imagine today. I picked carbon capture because it's a pertinent problem. The government is investing a lot of money to do carbon capture from flue gas and air, and it would be silly on my part not to use my materials to address that in the short term until our society is conscious enough to do the ideal solution. But I think that civilization, you can't stop science, and you have to advance. That's how we build economies and create livelihoods.
But lots of people want to store the CO2, so if there's a way to capture it, and
well, that's
throw it away.
That's
well,
what
not throw it away.
Well,
but
wait.
The oil companies want to put it back in their wells to increase oil harvesting.
But we're going to need carbon. We're going to run out of carbon if you think system-wise.
I want to talk about if you want to talk about carbon capture, sure, we can capture it, but very soon, already you can modify bacteria to turn CO2 into fuels and starting materials that go into pharmaceuticals and many things, proteins for food and things like that. So, So, I think that it's not as bleak. I think there are a lot of secondary effects that are very, very important to that problem if you want to just talk about CO2.
I have two responses, but take your questions, and if you have holes, then I'll come back with them.
Okay. Why don't we start with your question?
Hi, my name is Isabella. I'm a postdoc in the Division of Applied Microbiology here in Lund University. And still on the same topic, my question to the speakers is, do you think nowadays the research community is addressing the right research questions to solve climate change and implement a circular economy? And if it not, and if just partially, what should we do? What should we focus on?
I think we will start with you.
That'll give me the opportunity to take one of the points I wanted to just make, and that is, no, I mean, I think our societal narrative is all wrong. I think this focus on solutions is wrong. If you're dealing with a complex adaptive system, complex adaptive systems don't usually evolve in huge quantum steps or solutions. They evolve through many small changes. And the way your family's a complex adaptive system, and if it's dysfunctional, you don't just fix it. So the way we apply for our money, give me money for 3 years and I'll do this, and then before when you finish, here's the end of my report, I'm already looking for something else. Nobody is incentivizing us sitting and stopping and saying, what is it that I have here that can contribute to a transformation? And what are the barriers for that contributing, and how could it be upscaled? What difference could it make, and together with other things and so on? We're just not doing that. We're talking all the time about finding solutions, when in fact we need to be focusing on transforming. Okay. So I'm not sure we're asking the wrong questions, but I think we're looking for monumental things that aren't going to happen, and we're not incentivized to try and make this. We know perfectly well. For example, phosphorus. Phosphorus it's a limited resource. It's a fossil resource. We need it to grow our food. Right now, we've been getting it mostly from the Ukraine. Can't do that right now. So where is it? It's in China and it's in North Africa, which means China and North Africa have the key to our future food security. Now, is that smart? Probably not. We do have the technologies to be able to take phosphorus out of water and reuse it, but it can't pay. Now, one of the first things we need to do is to change our economic system so that it can pay to do the things we know we need to do. And that's like taxing all waste, not just CO2 and so on.
Okay, but since, as you suggest, we're not close to a solution, so is it riskier not to take any action or to take some actions with...
It may be riskier to do the wrong action.
Yeah.
It may be riskier to do the wrong action. So if you haven't thought it into a system context, then I think it's dangerous to do, yes.
But decreasing carbon dioxide burning is clearly something you could do. You could increase the electrifying society. That's a solution, but you could have to do it in a wise way.
Yes, I'm not disagreeing, Bengt.
Okay.
Catherine, I agree with you. I agree with your solution, but it's not practical in present global society. I think whatever you want to do, it has to jive with the possible.
But we're
right?
going at
We have a
this.
political system, we have a social system, we have an economic system. They're all interconnected, and we're here. We have an urgent problem, and short of a global revolution.
But you're going at this with the
it's-
assumption we're smarter than nature, and I don't think we are.
No, I think several of the speakers, including myself, although I didn't mention it, believe that nature is the greatest teacher and the most inspiring teacher. So I think we're all inspired by nature. I think we as scientists, and I don't think any of the speakers that so far spoke disagree with that. So you can't stop science, and science will find every avenue to solve whatever pertinent problem there might be. Carbon capture is not ideal, as already mentioned, but we have an urgent problem. We need to take CO2 out of the air. And as you said, once we take that, then the stuff from the ocean is going to come out, and we have to take that out. So,
But it's not the most clever solution. You need energy to do it.
well, give me a cleverer solution. You want to stop fossil fuel burning, and that's impractical,
So,
right? It's impractical. Who's going to stop that?
okay, I think we're going to have quite a few more questions on the exact topic, but before we go to the questions here, I want to ask Craig a question. I saw on your chart that Asians had the longest life expectancy. Now, are you talking about just in the United States or the world?
Well, that was U.S. data, but in most parts of the world, they outlive other ethnogeographic populations.
Their philosophy is much more along preventative lines. Is that in part due to, for that reason, or?
I think it's better genetics primarily. If you want to know how long you're going to live, look at your parents and grandparents. And the other big determinants are your mobility and your muscle strength. The combination of those things predict longevity more than anything. But you know, the Chinese populations have the lowest genetic variation of any ethnogeographic population. So it's a much more homogeneous genetic society. Direct African descent have the highest rate of variation. Caucasians are sort of in the middle on that. So it's all these things have to be taken into account, as well as diet and style of living.
Okay. We'll go to our next question.
Lorie?
Oh.
One from online for Professor Venter. When do you predict that the diagnosis technology will be available and affordable for the general public?
So it's available now, but not affordable. The only clinics that exist are one in San Diego and one in San Francisco, and there's also one in Beijing. They cost between $5,000 and $20,000, depending on the program you're doing. There's no reason for them to cost that. So the new ones we're building are in a not-for-profit center, and it really depends on how much AI can eliminate radiologists having to read the images. It could come down, a genome can now be done for $200. A full diploid genome is probably closer to $800. All the tests combined without the radiologist would be about $1,600. Executive physicals cost $5,000 any place you go, and the cost of disease outweighs these costs tremendously.
Okay, thank you. Could we take the next question?
Yes. Hello, my name is Olivia. I go to Procivitas in Malmö, and I have a question for Professor Richardson as well. So you obviously use a lot of models to collect data and understand the world, and one of the things you were talking about was materia and food falling down to deeper parts of the ocean where photosynthesis isn't possible. And I guess I was just left with the question, like, how is this measurable? Like, how do you, perhaps a bit of a technical question, but I didn't understand how you can even begin to create a model of this, really.
Well, we can actually do measurements of that sort of thing. And one of the big questions, one of the really exciting things is that on land, photosynthesis takes CO2 directly out of the atmosphere, and it gets stuck in life. And there's about 550 gigatons of carbon caught in life on land. In the ocean, there's very little carbon in life. There's only like 3 to 5 gigatons, 100 times less. There's just as much photosynthesis going on, and the only way that you can have a biological storage of CO2 in the ocean is if this material that gets created sinks to the bottom. We call it the biological pump. Lousy name because pump sounds like active, and it's not. It's things that are blah, 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 blah. And it's actually believed that in historical time, or geological time, that differing amounts sink down to the bottom and draw CO2 out of the atmosphere. So there's an awful lot of effort right now trying to figure out how much material falls down, and you can do it by having sedimentation traps and measuring it along the way. You can do it with uranium isotopes and seeing the changes in isotopes. There are numerous different ways that people are trying to do it. You can do it by analyzing sediment and how much organic material is in the sediment and so on. So there's a whole world out there that actually thinks the most important thing on Earth is figuring out how much is sinking through the ocean.
And that's why people want to do iron seeding to greatly increase the growth of the algae to have more CO2 sinking. But in my view, that's a very dangerous experiment we probably don't want to do.
Okay. Next, please.
I'm Werner from Gymnasie Katedralskolan here in Lund, and we're beginning to expand through space, and this gives us the opportunity to collect materials from space like metal and carbon. I wondered, will it lead to a problem if we gather these materials on Earth? Will it rub the balance in nature?
You're looking at me, so that was...
Go ahead.
It's really an interesting question because I was just at a meeting where somebody was suggesting that what we should do, because it's so inexpensive now to use rockets, is to take our waste and put it out there. And my point was, this is a closed system, so the more resources you put out there, there's less to play with. So it's an interesting idea if you could try and compensate some of it. I mean, I don't know what would happen, but you'd need to think of it in a system context and what it would mean. For many of those things, they're not in a reactive form, so it doesn't really matter. I mean, how much? What's worrying is when you, for example, with nitrogen and phosphorus, and actually our problem with carbon is we took it from a basically an inert form and make it reactive and put it into the environment. So if you're going to take minerals in that are not reactive, I wouldn't lie awake worrying about it, but I would think of it in a system context.
The space station does the opposite, takes all the waste on board the space station, packs it in stainless steel capsules and launches it back into the atmosphere. And so be careful when you wish upon a shooting star.
I like it.
Thank you.
Fine.
If we could have the next question, please.
Yes. Hi, I'm Evan from Polhem here in Lund. And Professor Werner, I was really fascinated by your results regarding the testosterone receptors. And I was wondering if you have found any similar results with, for example, estrogen receptors or any other hormone?
Well, it's been known for a long time, correlations with estrogen receptors and how treatable breast cancer is. And so that's one of the measurements that was always done early on, was measuring the estrogen receptor levels in breast cancer. But it's not a triplet repeat, so it has very different expression levels, and that's the problem with the triple negative breast cancers without very low estrogen receptor levels are much more complex for treating and harder to treat. So, but knowing the hormone levels and the receptor is essential for understanding what's going on biologically.
Both, yeah.
Okay. Thank you. Go ahead.
So hi, I'm Carl-Viggo from Posivitas in Helsingborg, and my question is perhaps particularly directed to you, Werner. I was thinking, if you manage to reduce cost of this screening so that it could be scaled, or would you then be able to scale this? You mentioned that like 5% of the population over 50 had some kind of a tumor, for example. Wouldn't this put huge pressure on healthcare, for example, treating all these people who you would now find?
No, because they have to get treated once they develop symptoms, which means they probably have at least stage 3, if not beyond cancer, quite often with metastases. The cost of the treatment goes up, the complexity goes up, the morbidity goes way up. So it's very inexpensive to treat a tumor at stage 0, stage 1, even stage 2 before it's metastasized. Usually, the medical system now is based on you having symptoms, which means you have to have enough advanced cancer to be causing you bone pain, some problem someplace to make you aware of the tumor. So finding them before you're aware of them usually means that they have not metastasized yet, and the costs are very low comparatively for treating them.
Okay. But do you envision that one does this procedure once a year or something like that? Or
So I do it twice a year, having had cancer. Cancer is not once and done in life. The biggest risk for disease is your age. It's not considered a risk factor, but it should be, because it's the biggest single risk as you age. Your risk for all diseases go up, but particularly heart disease and cancer. So, if you detect them early and get things corrected, you'll have a much better chance of living longer. The ideal thing would be to have your genome and your baseline studies done when you're young, because then you're your own control group for the rest of your life. And you're not comparing your numbers and your values to the rest of the human population. They're comparing to you, and are you changing? And so serial brain MRIs, we track people over years. You can see whether their brain's changing and by how much. You can see if tumors are developing. There could be debated how often should be done. Probably over 50, I would say once a year, unless you have been already diagnosed and treated with a major cancer. And also it's a way of tracking the metabolic disease with liver disease, and also progression of Alzheimer's, with all kinds of new things coming along to see if it could be delayed or prevented or treated.
Okay, so you see that this is scalable actually, and in spite of, and there would not perhaps be this tremendous new group of people searching for healthcare. So you see that there is a scalability here.
It's scalable if third-party payers are in countries that have a single-party payer have the motivation to do so. It'd be much cheaper than the existing systems.
I think the question is motivated. Increasing longevity moves things ahead, and you will have other challenges.
But you could change the retirement age to 75, for example.
We've already done that.
Right?
But this brings me to my problem with this, or at least my considerations. You're sitting in what would be your recommendation, for example, to the Swedish government, where life expectancy is about 10 years longer than it is in the United States.
Well, that would make it 95.
Well, it's later. I mean, I was going from the numbers you had here, but which was 74. But my point is that it's much less expensive here. The life expectancy is already longer than it is in the United States. And what worries me about all of this is it can only increase the North-South divide. It can only increase global inequality. And
so it's better to kill people off early then.
Well, I'm not sure. I'm not sure. I mean, I've outlived both of my parents at this point and still going strong. So I don't feel anyone's killing me off at this point. I mean, I'd love to have it for myself. I'm only thinking about what's at the end of the line in terms of global inequality and conflict.
But why does it have to be global inequality? I mean, the stuff is all portable, and it's a question of wills of governments to do it.
I think your philosophy shows that, for instance, the unfairness here. We saw that black and red Indians showed a higher mortality. If that could be amended.
Absolutely,
yeah.
absolutely.
We could go back to AI for a moment, since that's been a reoccurring theme throughout the day. And in some ways, AI could potentially play a role in that. But I'd like to hear, I think we should hear more from Professor Yagi about that, because he has one of the most positive outlooks of AI at this point and is actually using it.
But you too.
Yes, I can imagine, but let's hear.
I'm not using ChatGPT in my research yet, so
I'd like to hear about some of the potentials you see.
I can't figure out.
I'm an experimentalist. I like to experiment and push the frontiers of knowledge. And in this case, so far I'm looking at the AI as an important tool that could be transformative to what chemists do in the laboratory. And I showed some examples very quickly, but if I can put all the conditions under which people make compounds in front of my students, and which can be interrogated through machine learning or through other means, and the researchers now can make decisions based on facts rather than chemical intuition or some know-how passed down from graduate students or from PI to students. I think that they're going to make better decisions. The other thing is that what I've discovered is that even ChatGPT, which is not that great at doing things, but you can converse with it and train it to get really good at this specific thing you want, and just with minimal effort in the grand scheme of things, you can get it to look at a much larger reaction condition space, to explore much larger reaction condition space than what, let's say, a researcher might do, because they're basing a lot of the decisions that they make based on chemical intuition. So I think that that's one very important factor. Needless to say, you can do this much faster than if the researcher had to do this from scratch, much faster. I gave the example, crystallizing moths and coughs, I made it look easy. For some people it's easy because they've spent years in the area, but if you're new and you want to crystallize a moth, maybe if it's carboxylate moth, you might be able to do it much faster. But if you decide that your linkage is pyrazolate or some other functionality, you're going to be in the lab testing different conditions, probably for 2 years. But I showed you examples, again, with just ChatGPT, that you could speed that up to 2 weeks. So in many ways, I see AI as being transformative to our day-to-day. Needless to say that in the fullness of time, when we have databases and big data, which, by the way, ChatGPT can also do that, all should be supervised and, as I said, collaboration with the human to make sure that it's not hallucinating and it's not doing things that you don't want.
Which is about a third of what ChatGPT produces.
It depends on what you're doing. It depends how you train it. I find that the emerging scholars are much better than the more senior people in conversing with ChatGPT and getting it to do things. But that's one approach. The other approach is to really develop the basics of Gen AI for what you're doing. For example, for me, it's discovery of new materials, correlating those materials with applications. Then you need to put into your machine learning algorithm some information that makes it more intelligent. And so that's a huge area that needs to be developed. We have to develop it for the survival of our field.
There's a real nice study that just came out of Caltech looking at pathology slides of people that had cancer. The slides were 10 years old, so they knew the outcome. It was trying to predict from looking at the tumors which patients would go on to develop metastases. Pathologists, the best they could do was 50-50 guessing. The AI algorithm with just small test sets was able to get to the 80 or 90% level. But it was mentioned earlier, it's often difficult to go back and understand the decision-making process. Nobody can tell looking at the slides how the algorithm was making the choices, but it's a tremendous step forward that no pathologist can make those decisions. So it shows the hope for improving pathology and lowering the cost and getting more accurate information out of it. But the other study they did showed that, you know, if you talk to AI people, they always say you have to have massive data sets. And so this has just gotten disproven that if you have really expert data sets with experts providing the information on them, true experts, it can be a data set as small as 50 with real experts.
Yeah, and it's not only pathologists that will teach the AI, it's also the post-mortem results. You know, you have the answer. My father was a pathologist, and he said it takes 15 years before you learn how to interpret.
So, Catherine, why don't we hear about how AI is being applied to some of the climate issues that you mentioned, and then we'll take your questions.
I have no idea.
Okay, we'll take a question then.
It's in the cloud.
Hello? Sorry, I'm a bit nervous. I'm Oliver. I study at Ystad Gymnasium. And I was just wondering, since AI is a recurring topic, do you ever think that AI will completely replace humans?
For what?
Everything.
No.
Ever.
It's going to have a hard time making babies.
That's easy.
Fair enough.
Omar, do you?
It's hard to see it at present. I think it will replace a lot of the stuff that we do, but humans are really creative creatures, and they think in chaotic ways and unexpected ways. It's very complex. Our creativity comes from a lot of complexity, and it's not clear that it could be modeled, because if you just look at the speeches that we had, and each person's discovery was completely different. So I don't know. I'm not willing to say that we would be replaced, but certainly a lot of the tasks that we do may very well be, you know.
Okay, thank you. We're going to, Professor Medal, as soon as you get the microphone.
I think we need to make one thing very clear, and that is that a computer is not a brain. And a brain has a sensation, sensual knowledge about itself. It has a consciousness, which you will be able to simulate in a computer, but you will never be able to create it. So I think that it will take a very, very long time before artificial intelligence will become functional the same way as a brain is.
I'm going to say something really strong. I would say anything that stops experimentation should not be tolerated in science. And I think one of the people who gave a speech early on is very objective, and there is no emotion or sensation. I think that makes for a great scientist. So I am a strong believer in experimentation and pushing science to its limits.
What about gain of function pathogenic viral work?
You can answer that.
Well, you said nothing should be stopped. That's,
Well, I mean, I think when it comes to that, then there are some ethical things that have to be considered, obviously. I mean, we don't do things blindly. But I think the acquisition of knowledge should not be hindered. I think,
You should not stop science. I agree fully. Yeah.
Okay. Let's take the question here, and then we'll go over there.
Hello, my name is Louis, and I come from Gothenburg, and I go to Hvitfeldtska. And this is a question directed towards Richardson, and it's about, well, in school we speak about ocean acidification, and we briefly came along across the term of the point or tip of no return, which, you know, is about the ocean continuously releasing carbon dioxide into the atmosphere, continuously heating up in a cycle. And this is a point that I suspect that we will reach at some point, and it will undoubtedly lead to some extinction of creatures with organite shells in the sea. And I'm just curious about what you think. How would that affect the ecosystems? And most importantly, how would we as humans react to this phenomena?
That is a really loaded question. Thank you.
I know you can speak.
First of all, we don't give the ocean the respect that it deserves. And the ocean can tell us an awful lot. First of all, I'm really unhappy that it didn't get more, or it doesn't get more focus in the media. But if you took the temperature of the ocean since the 1970s, every year, the global ocean from 50 north to 50 south, it goes up, the next year, they overlap, and so you end up with a band of spaghetti. Until the middle of 2023, bing, we suddenly jump up 0.2 degrees in average warmer. And it stayed up there. We've got this big jump, which has a huge effect. That's why we're hearing about the Great Barrier Reef and the great bleaching that we have at the moment. And the really scary thing about that is that nobody knows why. Oh, yes, there was an El Nino, but there's been El Nino before since the 1970s. Oh, yes, there's climate change, but there's been climate change before. Oh, yes, there was less wind over. Nobody can totally explain it, which means that our models, I mean, nobody in 22 with our models said, hey, something big's going to happen in the ocean next year, and that's, by the way, where over 90% of the extra heat is stored on this planet. And what that tells us, and you know, people have said to me, does that mean our models aren't valid? Yes, our models are valid. They give our best understanding of how the system reacts. The fact that the system's doing something different tells us we don't understand the system very well. So there's a lot of things we can learn from the ocean. In terms of ocean acidification, yeah, I mean, it's already well known that if the world achieves the goals of the Paris Agreement, and nothing indicates that they will. But if they do, we'll still lose the coral reefs. But nobody cares.
Well, temperature change is more important than acidification.
Yeah. That's why I started with it. That's why I started with that.
1 degree temperature change in the Indian Ocean resulted in all the white sandy beaches and the Seychelles from killing off a symbiotic bacteria that kept the coral alive. Just 1 degree C.
Yeah. But my point is that there's an interaction between both temperature and acidification. If you look at pteropods in the surface, it's the acidification. Or if you look on the west coast of the United States where they're trying to raise oysters, baby oysters have paper-thin shells that when you acidify the water makes it very difficult. So we are seeing also economic effects of acidification now. The point is the ocean is really, really very important to us. We're not very interested in the ocean. We don't understand it very well. We would rather go into space and understand what's going on there than understand the ocean. But in terms of geological time on this planet, the ocean has been the regulator of climate, because when you went from ice ages to non-ice ages, you moved 80 parts per million CO2 from the ocean to the atmosphere and back again. And you can't explain that alone on the basis of only physics and chemistry. We need biology, and we have so little understanding of that.
Well, by the way, the book that I showed was about our ocean expedition, that before we did this, oceanographers thought there was very little biological diversity in the microbial populations in the oceans.
I'm afraid you and I are probably pretty close in age. And when I started studying, there were no bacteria in the ocean. The only ones that were there were the ones that might have run in from land.
They number them one at a time in the Sargasso Sea. They were up to SAR 11 when we did our shotgun experiment to show that there was roughly 2,500 species there that they had missed.
Yeah.
So,
Thank you. If you don't mind, we'll take the question that's over there somewhere.
Hi, my name is Evelina, and I'm from Landskrona. And I have a question to both Professor Jargi and Professor Richardson. So, how can business and industries be encouraged to adopt more sustainable practices? Thank you.
How can what?
How
Industries
can
be more encouraged to adopt more sustainable practices?
Yeah.
Well, I mean, I think that there's now progressively this move towards a circular economy. And I think that's a very positive thing. I think we need to do more of that. We need the governments to fund programs that allow you to do that scientifically, to address those challenges. I think at the end of the day, society has to want that, okay? CO2 capture was not very interesting when we first started working on it back in the mid-1990s, okay? And now everybody is in agreement that we have a CO2 problem. So I think if we can do this faster, we might avoid some of the bigger problems that lie ahead if we just wait until it's facing us right here.
Okay.
Yeah.
I think in addition to their economic reporting every year that they should have to do both climate and biodiversity reporting. And for metrics on biodiversity, you could use area or biomass that is used in your value chain. And of course, you've got greenhouse gases as your. So I think they should have to report that. I think they should be making goals for how to reduce their impacts. And I think we need to be legislating in order to make it be more expensive to not be better in those areas.
Thank you. Dr. Venter?
So changing a little bit, Professor Jargi, I was really incredibly impressed with your potential for water purification. I think that's far more important than CO2 capture. So how economic is it to produce those things? Because the ones in Africa, they're all based on stills, whether they're vacuum stills or something else that require lots of energy.
Yeah.
I mean, it looked like just a wonderful passive system for doing that. So it's like that could be one of the biggest breakthroughs in health.
Yeah, certainly. So these adsorption systems using MOFs are designed to take water from not just low humidity, but also higher humidity, without this cooling that these systems that are that you describe are operating on. When you have cooling, like refrigeration cooling, you're using a lot of energy.
Yeah.
With these systems, the only, let's say, the cost of energy is really the heating of the MOF in the electrified, if you want to. But the non-electrified is just working on sunlight.
But in southern Africa, you have a lot of humidity and a lot of heat. So
yeah, exactly. But if it's electrified, so you have the energy that you have to put in to take the water out. The fact that you have a hydrophilic, hydrophobic pockets allows you to use lower temperature, so that's a good thing. Second thing is air. Fans that push the air into the material, and that is about 80% of the cost of energy. So
how do you prevent pollution of the MOF?
It doesn't, well, first of all, the MOF, so let's say you have NOx's in the air, water sticks to the interior of the MOF much stronger, so that gets kicked out. Let's say you have dust particles, you can always have an air filter. A very inexpensive air filter.
So is the cost of this, is it scalable for?
Well, I mean, as far as the MOFs are concerned, BASF has demonstrated that they could be made in water in multi-ton quantities, and then at the end of this 6-7 years, if the MOF is really the cause, at the end its function is exhausted, you could add a strong acid to it and separate it into its constituents and then reassemble it in water with zero discharge, because all the starting material, their synthesis is perfected so that all the starting materials end up in your product, in the MOF. So, and concerning the cost of the MOF, for the electrified system is only using 200 grams of MOF. So I mean, it could be even gold, and you're using it repeatedly over six years. It's nothing. Yeah.
Okay.
The rest of the device is just made from off-the-shelf parts. Yeah.
Thank you. I'm going to give you the honor of the last question for today. Oh, okay, we're going to have two last questions. So why don't you go ahead?
Yes, my name is Ville. I'm from Nordén. I have a question about MOFs. When the MOF binds to water or water binds to MOFs, how does the abilities of the molecule change? Does it change in boiling point, for example?
That's an interesting question. It's hard to say what is the state of matter of water in the pore. I mean, it's hydrogen bonded, but it doesn't have the structure of a fragment of ice, right? There are 14, maybe 15 different structures of ice. It doesn't have that, but it is hydrogen bonded. The key here is that water molecule, the very first water molecule, sticks to the most hydrophilic adsorptive site. And what I forgot to say, as usual, I forget to say the most important thing sometimes, is that water molecule is a seed onto which other water molecules bind from air. And so you see that it's a cooperative behavior, just like oxygen with hemoglobin. And that's the perfect kind of behavior you want, so that you can take the water out by varying the conditions slightly with pressure. You can take the water out. If it was shallow, then you would have to vary the conditions widely, and that's more energy. So it really is a cooperative phenomena, and the evolution of water in the pore has to do with that seed water that always stays in the MOF. Because to take that first water out is going to cost you more energy, and why should you do that?
Yeah.
So
it's hydrogen bonding.
It's called hydrogen bonding, but also it's, somebody said water, I think it was Jean-Marie Lehn, said water molecule is the same here or somewhere else. And yes, I understand what he's saying, but I think the first water molecule is really different because of the way the molecule interacts with the surface, you see. Mm-hmm. So I think the interaction between molecules is so important to consider. Sometimes we think of molecules as isolated entities, but really a lot of their properties come from how they interact with each other. So I didn't answer your question. I don't know what is the state of matter of the because it is hydrogen bonded. In ice, it's hydrogen bonded, but it doesn't have the same structure.
Thank you.
Yeah. Thank you.
Okay, go ahead.
Hello. My name is Niels. I'm a PhD student here at the Chemistry Center in Biochemistry. And I just want to say, for all the three speakers, the last three talks, I found very inspiring, and it changed my mind a little, which is always good. And I find the slight professional disagreement here also extremely informative, to hear such a discussion between eminent scholars that slightly disagree. In our field we have AlphaFold 2. I'm doing computational protein design. And we had a complete paradigm shift from our physical-based, statistical-based models that gave some kind of insight to completely black box AI things that greatly outperform our old methods. And the thing is I really dislike the term AI because it's not intelligent. It's machine learning. That's, I think, what we should call it instead. I wanted to ask about the choice to use ChatGPT over other, what I believe called text extraction methods or information, or text interpretation or something. That's a whole research field that I think also has been a long history. And it was only until ChatGPT sort of was available to the masses, more or less, that it really became like in a common consciousness that this AI, these generative models, sorry, I call it AI again, that these really have very interesting properties. But I wanted to ask, have you considered the other non-large language model-based AI pipelines that to do, for example, this task of information extraction from scientific articles?
Yeah. I mean, those models, they work, but they're very, very slow, and scientists couldn't use them, like researchers in my lab, let's say, couldn't use them because you have to go back and do heavy reprogramming to make it suitable for that specific task. While now with ChatGPT, all you have to do is converse with it through prompt. And now we are collaborating with a computer scientist who can even automate the prompts for you so that they are more perfect than what a researcher would put in. So, and that facilitated access of this ability to mine information to anyone in my lab. They didn't need to know programming. In fact, ChatGPT will reprogram things if you want. It can reprogram our robot for various purposes. So this is what I'm talking about. That is I don't want to say a revolution, but there is something there that is shifting dramatically the way we do things in the lab, the way we do research. Yeah.
Okay, thank you. So
thank you.
We're going to have to stop soon because some of you I know have to get to the airport. However, I'm going to ask each of you, the speakers, to summarize just in a few sentences where you think we're headed in the future. And I'll start with you, Omar, because I know you have to leave first.
Well, I have a very positive outlook about the future because I still work with students no matter where they are. I've been to many universities, I've lectured in many universities. No matter where they are, they're very interested. They're very interested in the future, they're very interested in doing the right things, and they're smart. And I do believe in the power of innovation, and humans have demonstrated over and over again their tremendous capacity for creativity. And so don't underestimate, that's why I think it's hard to prejudge the future, because we're not taking into account this tremendous talent for creativity that humans are capable of.
Thank you.
So I have a very positive outlook.
Dr. Venter?
Well, like most scientists, I'm an extreme optimist, except when I look at the political situation in the United States, which makes a pessimist out of almost anybody, with at least 40% of the country being anti-education, anti-intellectual, anti-science, anti-evidence-based decision-making, anti-truth. Societies have been there before, but we're close to a tipping point that it doesn't matter how many brilliant scientists there are, if we're outnumbered by the ignorant masses, the outcome could be far more bleak.
Catherine might have to add an additional tipping point to her chart.
Well, actually, that's a good point. But first of all, I'm sorry I started out by sounding like the sour old lady on this one. I actually think we agree. No, I actually think we agree. I'm incredibly optimistic because I simply cannot believe, although the evidence doesn't look good, I have to admit, but I simply cannot believe that humanity would be so foolish as to ignore the knowledge that we have. And I do believe that knowledge is power. You seem to think innovation is power. I think knowledge is power. I think we're at a really, really pivotal position in our understanding of our relationship to knowledge and the world. I think back to Darwin in 1859, and no, I wasn't here at that point, almost, but not quite. And his point was, we're not better than all other organisms. We're organisms just like all the rest. And there's still people that don't get it, but most people have gotten there. Where we are now is I think in terms of we're not better or smarter than the ecosystem. We're not going to be able to do it better than the ecosystem that we're a part of. We have to respect that we're a part of it and learn from it. And I think that's what we're doing. And I honestly, I'm both a mother and a grandmother, and I believe there's a future for my genes.
Excellent point.
I think our host should have the last word.
No, that's not, he will have the last word.
She promised.
I figured he would anyway.
He always has the last word. But I'm going to just say thank you, and then we'll save the best for last. How about that? So I just want to say a final thank you to everyone who's participated in the program. I believe we have a lot to consider and hope that some of the messages you've received over the past 2 days offer new perspectives and means on how we as a species can best navigate our pathways forward together. I need to thank Lucy, whose discovery 50 years ago by Professor Johansson got us all to thinking in different ways, and in a way brought us all together today. I want to thank again all of our excellent speakers, whose research, discoveries, and the willingness to share their knowledge offer means and possibilities for the future. Thank you again to our hosts, Lund University, the Royal Physiographic Society, our sponsors, volunteers, and the audience who together made this program something more than was possible on an individual basis. It is the work of all together from the many different backgrounds and places that are gathered here that will serve to predict our collective futures. So thank you all for being part of this,